Welcome everyone to Net 311, how AWS Global Accelerator improves performance. My name is Dennis Marinas and I'm an engineer on the AWS Global Accelerator team. Before we begin, just a heads up that this is a 300 level advanced technical session. This means that I'll be assuming you've worked with AWS Global Accelerator before and are at least somewhat familiar with the TCP/IP protocol suite. I'll still give a bit of an overview of AWS Global Accelerator, but mostly we'll be going to deep dive into exactly how Global Accelerator makes your internet-facing applications perform better than they currently do. So what do you get out of watching this session? We'll mostly be covering network topics that are outside of a common developer's control, such as how any network, or in this case the internet, will impact how your customers experience your applications, why fronting your application with an accelerator will make it perform better, and we'll go through some tips and tricks on how you can prepare your client and software setup better for dealing with the unpredictable internet weather. So what is AWS Global Accelerator? Global Accelerator is a networking service that sends your users traffic through Amazon Web Services' global network infrastructure, improving your internet user performance by up to 60%. So what are some of the key features of Global Accelerator? Firstly, your accelerator's IP addresses are fixed for the lifetime of your accelerator. They are not shared with other customers, and you can enter them in firewalls, DNS records, or in legacy devices that don't even support DNS. Secondly, by ingressing your user's traffic into the nearest edge location, you bypass a lot of the global internet congestion and keep your packet loss, jitter, and latencies consistently low. This will result in performance improvements of up to 60%. Thirdly, AWS Global Accelerator can perform a worldwide failover away from an unhealthy endpoint in less than 30 seconds, and that is independent of DNS TTLs or ISP resolvers not even respecting your DNS TTL. Fourth, AWS Global Accelerator allows you to add or expand multiple AWS regions behind a single accelerator, or even migrate traffic from one region to another, all without ever changing your public IPs and DNS records. And lastly, all accelerators are protected by default from distributed denial of service attacks with AWS Shield. So let's go through the basic building blocks that make up an accelerator. First, we'll start with your two static IPs. These IPs are in two separate network zones, which function similarly to availability zones. We then create TCP or UDP listeners. These are the ports or port ranges that your internet clients will connect to, such as port 80 and 443. And finally, we add one or more resources, such as ALBs, NLBs, and EC2 instances behind each listener. These resources can be from multiple AWS regions, and Global Accelerator will automatically route the closest resource for each client connection. So AWS Global Accelerator uses the global AWS backbone present in 88 cities across 44 countries around the world. And Global Accelerator is currently in 83 out of these 88 cities. So I've enlisted the help of AWS's favorite employee, Pecky, to help me walk through the use case we'll be deep diving into today. In this scenario, Pecky works as a support engineer for a very popular app that's hosted on AWS. Today, just like every morning, Pecky starts by checking out his CloudWatch dashboard that has all of his key metrics on it. Everything looks fine, there are no errors or strange spikes last night, and all latency numbers are green, so Pecky is happy. Next, Pecky opens the ticket queue and to his surprise finds a message from one of his customers. This specific customer is happy with the app, but is saying that for him it loads slow and asks Pecky to make it faster. Pecky is initially a bit confused. After all, he just checked the dashboard and everything looked fine here. So what's going on? In order to really figure out what's going on, I'll start by giving an overview of the app that Pecky is responsible for. I've on purpose created a very small one, since we will mostly be looking outside of this app. Pecky's app consists of an application load balancer fronting a single Lambda function, and that's it. Both the ALB and Lambda function are configured correctly, and Pecky's code is properly optimized, taking only about 5 milliseconds to run. We'll discover that the root cause for Pecky's situation is actually outside of the AWS region. We tend to draw the internet that connects our users to our applications as simply a bubble or a cloud between the two, but that's of course not true. Sometimes when we have a global user base, we'll take a step back and draw them and our app on a map, but we'll still just draw straight lines from where our users are to the AWS region that our app is running in, and we'll call it good. When you actually take a close look at how the internet looks in detail, it's a very different picture. Even this is a very simplified depiction of the internet. Each of these points represents a network hub, and this map only shows a few of the very largest ones. Each hub has multiple carriers connecting to each other, and each carrier can have a dozen or sometimes even hundreds of routers at that location. Everything is connected via a nearly endless number of variety of cables, some of them a few meters long, and some of them literally cross oceans. So how does all of this look from the perspective of an AWS region? The internet currently consists of about 70,000 individually operated networks, and this graph only shows the largest ones. You'll see that while 16509 Amazon's ASN is well connected, there's still quite a path that some of Pecky's users need to traverse in order to get to the AWS region that's hosting his app. So why does all of this matter? In short, performance. The internet rarely goes into a straight line, and it can take many networks for Pecky's users to reach his app. If you do the math for the common fiber types used to build the internet, you'll find that you can only travel about 100 kilometers or 62 miles round trip per millisecond. In short, it takes time to cross significant distances, and these latencies will add up. Each individual hop or router can also impact performance, as each one is a chance for congestion, jitter, or even packet loss. Not all communication goes through fiber optic cables. At home, most of us have Wi-Fi, and on the go 4G and LTE are quite common, and those wireless technologies also add latencies. To give you an example, from my home in Seattle to our US East 1 region, it takes about 90 milliseconds to do a round trip via Wi-Fi and about 115 via 4G. That single echo packet goes through about 30 routers before it makes it to the AWS region. Going further away, latencies can easily reach a third or even half a second for a single round trip. So let's look at how all of that latency affects the total response time that Pecky's users get from the app he's hosting on AWS. In this example, we'll follow along with what's happening inside the TCP/IP stacks of Pecky's customer and his ALB, so we can understand where most of the observed delay comes from. I've chosen a round trip of 80 milliseconds, a little bit less than for my home, because it makes the math easier. We'll also skip any latencies related to DNS, because that's generally cached in either your Wi-Fi router or your ISP's name resolvers. When Pecky's client code executes a request, the TCP stack of that user will start by sending a SYN packet to his ALB to establish the connection to send that request over. In this scenario, that takes 40 milliseconds. The ALB will then respond with an ACK and send its own SYN, which takes another 40 milliseconds to arrive back at Pecky's client. The TCP stack will then acknowledge that SYN and immediately send out his request. In this example, I'm making the assumption that the request fits inside one MSS, which is generally around 1400 bytes, but large headers, cookies, or request payload could change that. At 120 milliseconds after we started, the ALB has received our request. There's a lot of things happening at this time, like ALB parsing your request, handing it off to Lambda, which then finds or provisions Pecky's function, runs his code. Any downstream service calls such as DynamoDB or S3 requests that his code makes are executed, and finally Lambda returns the output of his function to the ALB. I've budgeted a total of 5 milliseconds for all of this to happen, and this 5 milliseconds is the value that Pecky originally saw on his CloudWatch dashboard, and is what made him say that everything inside his app is working fine. So let's assume that Pecky's Lambda returned a response of about 9 kilobytes. That can be a single HTML web page, a JSON response for a list call, or the contents of a single message. Here we get to the root cause of Pecky's performance issue, TCP congestion control. TCP is limited by the underlying network in the size of each data packet that it can send, and that limit is generally around 1400 bytes. So TCP sends out the first 1400 bytes of the HTTP response and waits for the other side to acknowledge that. Now that we've gotten a successful acknowledgement, a few things happen. The most important one is that the TCP congestion window starts opening up because we've gotten a positive signal from the receiving side that our packet arrived successfully. This means we're doubling our congestion window to 2, and thus we can send 2 packets worth of data this time. Our progress is currently 4,200 bytes, and it took 245 milliseconds for the client to have received those bytes. Next round trip, we do the same thing again. Our window scales up to 5,600 bytes, or 4 packets, and that's enough for the ALB to send the remainder of Pecky's 9K of data. All up, it took 325 milliseconds from the start of the request to Pecky's user having received this response, and only 5 milliseconds of that was Pecky's own code. That means, in this case, 98.5% of the time his user was waiting, it was not due to his code. So, TCP congestion control. Why is it taking 98.5% of our total response time? This comes from the fact that the internet is fundamentally a shared resource, and that both the sender and receiver of data know nothing of the networks, routers, and their capacity and utilization in between them. TCP congestion control is designed to automatically detect how much available capacity there currently is available between the sender and receiver, and adjust the data rates to match that. While doing that, it also tries to be both fair to other users of the network, so that your little brother can play his video game and at the same time your mom can watch Netflix, while preventing the same data streams from overwhelming the network in between. I previously said that the distance and multiple hops affect performance. So let's see what happens to our previous example if we lose a single packet. In this case, one of the data packets gets lost. A modern TCP stack would use selective ACK and tell the sender that it received packet 3 but hasn't received packet 2. This would result in two things happening on the sender. First, it would reduce the congestion window to the previous value, down from 2 to 1, because it assumes that the packet didn't make it because of congestion, and it would resend packet number 2 because it has a window of 1 packet right now. From here on, things are similar as before. Each packet gets acknowledged, we scale up our window as normal, and our congestion window ends up being 4, but we only have 2 packets worth of data left of our 9K of response, and in this time, all of the transmission took 485 milliseconds to reach the user. So in this example, a single lost packet caused our total transmission time to increase from 325 to 485 milliseconds, an increase of nearly 50%. So after learning all of this, Pecky starts looking for ways to improve his user's experience, and he decides to give AWS Global Accelerator a try. He first uses the speed test at speedtest.globalaccelerator.aws, and the results look promising, so he decides to enable Global Accelerator for his ALB. He navigates to his ALB, and on the Integrated Services tab, clicks Create Accelerator. He types in a name, and a few seconds later, his accelerator is provisioned. The accelerator page then shows all the details of the accelerator that is created. Pecky then uses the Route 53 console to change his existing alias record to point to his new accelerator instead of his ALB, and Pecky is done in less time than it would take to watch a funny cat video. So why is Global Accelerator faster than using ALB directly? This is the same view we previously had of an AWS region, but in this time of AWS Global Accelerator. The main difference you'll see is a lot less intermediate networks, and that's because AWS Global Accelerator uses Anycast. This technique allows us to announce the same IP space from every edge location on the AWS backbone network, so that no matter where your customers are on the internet, they always prefer the nearest AWS edge location. And this means that Pecky's users' traffic enter the AWS border network much closer to them than it previously did. Less networks means less kilometers of cable to travel through, and less routers means less chance for congestion, jitter, and packet loss. And this eliminates a lot of the internet weather effects on Pecky's users' experience. So AWS Global Accelerator is positioned on the border between the public internet and the AWS backbone. These two networks have very different characteristics, and being able to optimize the TCP connection independently for these two different networks is core to the performance improvements that AWS Global Accelerator brings. Clients on the public internet have various connection speeds. Some of them have fiber to the home, and some of them are a dial-up or satellite connection. The AWS backbone, on the other hand, has consistent high throughput between all of its regions and edge locations, consisting of multiple 100 gig links that are actively monitored and traffic controlled. Because of the many locations that AWS Global Accelerator is present in, we are generally very close to the internet client, and this results in a very low round-trip time between these two systems. Because of that, because most of the connection is going over the AWS backbone, most of the round-trip time is now spent between AWS Global Accelerator and the AWS region. It's not uncommon to see the AWS backbone being anywhere between 75 and 95% of the total connection path. And that round-trip time distribution is a good thing because the public internet also has a higher probability of experiencing the events that cause TCP congestion control to become active, because congestion control mostly relies on round-trip time signals to recover. Having a much lower round-trip time also allows for a much faster recovery. And since we fully control our backbone links, we can also use features that the public internet doesn't support. One of these is called jumbo frames, and this allows us to increase the amount of data in a single packet from about 1400 bytes on the public internet to over 9000 bytes on the AWS backbone. This allows us to pack nearly 6.5 times as much data in a single round-trip time. So in summary, the TCP connection between AWS Global Accelerator and the AWS region is optimized to take advantage of the consistently high throughput AWS backbone, and the connection between AWS Global Accelerator and the internet client is optimized to best deal with the varying and unpredictable nature of the internet. So let's look at the same example we used previously, but this time after Pekki added AWS Global Accelerator to his ALB. AWS Global Accelerator is about 10 milliseconds from the customer and about 70 milliseconds from our ALB. The overall latency is still 80 milliseconds. We can't change physics. So once AWS Global Accelerator receives the TCP SYN from your customer, it does two things. It immediately answers the handshake with a SYN ACK and builds a new connection to your ALB. The customer handshake now completes in 10 milliseconds versus 80 milliseconds previously. Your customer then sends their request, at which point AWS Global Accelerator will buffer that until the backend TCP connection completes. If it would take multiple round trips times to receive the request, because it is larger than the initial MSS of about 1400 bytes, that would also go faster. Once the backend connection completes, AWS Global Accelerator will forward your request to the resource behind it, in this case the application load balancer. Your code runs like it did previously, taking 5 milliseconds to return the response. And here you can see the benefit that jumbo frames bring. Since these frames are 6.5 times larger than normal, they allow most requests to complete in a single round-trip time. The downside to them is that they don't work on the public internet and you need to own the entire network path between the two endpoints before you can enable it. In our example, it only takes a single jumbo frame to send Pekki's entire response from the ALB to AWS Global Accelerator. Now that AWS Global Accelerator has the full response, it will send this to the client similarly to our previous example. As we go through the round trips, you'll see that the difference between 80 milliseconds round trip previously and only 10 milliseconds via Global Accelerator really starts to matter. Without Global Accelerator, it took us 245 milliseconds to reach the first congestion window scaling event, and with it we get there in only 165 milliseconds. And after 175 milliseconds, we've now successfully sent our 9K response to our client. In this example, AWS Global Accelerator improved Pekki's performance by 46%, but Pekki notices that the performance improvements depends on how far his clients are from the AWS region his app is in, and for clients further away, he actually sees performance improvements up to 60%. The next morning, Pekki looks at the ticket queue again and finds another message from the same customer. The customer is happy that his favorite app suddenly performs a lot better and thanks Pekki for all of the hard work he must have done. Now we'll get to some of the things that you as a developer can do to further improve your customer's performance. If you don't measure your client-side performance, you're only looking at half the picture. Our public SDKs can be configured to publish CloudWatch metrics, and our AWS Amplify network is a good fit for browsers or mobile apps. Reusing your SDK clients and HTTP connections is another one. This is because each SDK client will maintain its own HTTP connection pool, and by doing this, you'll prevent some of the startup delays from our examples. The TCP handshake will already be done, and your congestion window will have already started scaling up. Browsers can do this part automatically for you, but for mobile apps and scripts, it's your responsibility. Cookies are one of those things that we set and forget, but as they get sent with every request, they do impact your request size. This might mean that you need multiple round-trip times just to send the request, and your Lambda code doesn't start executing until your request has been fully received and parsed by the ALB. And lastly, given that AWS Global Accelerator IP addresses are static for the lifetime of the accelerator, you don't need to have low TTLs on them. This can help with remote clients or for endpoints that don't receive continuous traffic. A TTL of 1 day or 86,400 seconds is sufficient. So let's recap what we've learned in this session. We've looked at how the internet impacts how your customers experience your application, why fronting your application with an accelerator will make it perform better, and we've looked at some ways that you can prepare your software and client setup better for dealing with the unpredictable internet weather. That was the whole session.